And again, and again, and again, and we're back again. Today we gotta do stars. We just left off talking about the universe and the galaxy. Now we're gonna get a little bit smaller. Gotta do with stars. Why? Because that's a star, the one that's behind the clouds somewhere today. So we have to talk about how do stars form? What are they? And how do we analyze them for different variables? Okay. One of them being temperature, luminosity. All right, let's get into it. So stars, giant balls of gas. Kind of how I feel sometimes, a giant ball of gas. But anyways, the light that's produced from these things are due to a process called fusion energy. Okay, so fusion energy is the combination of two lightweight elements that are then combined and forced together and stuck together to form a newer and heavier element. What we're talking about is two hydrogen atoms that are combined together to form helium. All right? Now, in order for that to happen, you have to have extreme temperatures, extreme pressures, and a lot of that is all due to gravity, taking the gas in the area of the galaxy or the nebula and causing it to collapse and coalesce until it starts building up more and more pressure, and all that gas is bouncing around and generating friction and heat, and boom! You end up getting fusion. That fusion is what then gives us all that light and all that heat and all that radiation for Earth. So it is not a light topic to take on. This is going to be pretty heavy in terms of how important it is for all of life on this planet. Okay. Now, how do we start analyzing stars? It's not just our star that's undergoing fusion, it's also all the other stars that are in the sky. And how do they all kind of vary in different ways? Some are big, some are small, some are the size of almost our solar system. And so we want to talk about how there are two major variables: temperature, luminosity. Temperature is going to be how hot this thing is. Luminosity is going to be how bright this thing is compared to the sun. So luminosity tends to be that the bigger and brighter these things are, they're a higher luminosity. So a higher luminosity doesn't always dictate necessarily a higher temperature. Okay? But a higher temperature does sometimes result in a higher luminosity. So let's take a look at the temperature scale here in terms of hottest stars and the colors that are associated with them, and then we're going to dive into the reference tables and take a look at how the graph works out there on page 15. So about 95% of stars end up on something called the main sequence. The main sequence is an area where most stars reside based on their temperature and luminosity conditions. Okay? So we tend to have first a scale of temperatures from red to blue. So red being coolest, blue being hottest. This scale is actually reversed on our graph, so I don't want you to get overly attached to this right now before we take a look at that page. So with that said, let's go to the page. Here we go. So characteristics of stars. I would like you to call this also the HR diagram. So HR stands for the Hertz. Whoa, Carl, you're really messing with me this time. The Hertz-Sprung-Russell diagram. And this is purely a plot of temperature versus luminosity. This is not the map of the galaxy. This is not the map of the universe. This is purely where these stars end up on the graph. So here we've got red, cooler. We've got here blue being hottest. We have luminosities that scale down very, very small, multiple decimal points. And then we have luminosities that get as high as 1 million. Well, 1 million what? Well, there isn't exactly a direct unit, but we are always comparing everything with the sun. The sun, for us, is like our ruler in space. Not like king, but like literally a measuring tool for us to measure out the luminosities of other types of stars. And it also is going to be a distance tool for us too, like the astronomical unit. So we use its brightness and the distance to it to help us measure and gauge everything in our galaxy and universe. All right, now let's take a look at these scales down here. Very similar, the gaps in between our values are not uniform. They are logarithmic, to say the least, and these gaps will have to take into account that the scales are different sizes, the interval sizes in between them, when estimating temperatures, colors. Same thing here with luminosities. We're going to have to approximate where everything is. So everything in this area counts up by ones, everything in this area counts up by tens, by hundreds, and so on. Down here, we have to just kind of estimate. So this is 2,000 to 3,000 Kelvin, the absolute temperature scale. In between here would be 2,500. But we've got 4,000 and 5,000. The gap is smaller, so 4,500 is going to be a little bit closer to here. So there's a process of determining the value, and it's going to take you some time to realize that these gaps get smaller and smaller. So small that it becomes 11, 12, 13, 14, 15, and so on. All right? Now, it's like any other graph. We find temperature on our x-axis. We come up, we find our star with this circle and a crosshair in between, and that will give us our luminosity. And we have several names of stars within the HR diagram. We also have types of stars. So down here we have the white dwarfs. Here we've got main sequence. So everything on this band here is a main sequence star. We have giants, then we have supergiants. And those giants and supergiants, more specifically supergiants, can be blue or red. Most just giants are on the red side, and then main sequence can be the full spectrum, and our white dwarfs, you figure, are usually on the white in color, okay? Now, we have an indicator that we have small stars down here, large stars up here. So, with that said, what I'd like you to try to do is I'd like you to pause the video and attempt to do the questions on the next page. So pause it up and then we'll come back to talk about the death of a star and the life cycle of a star. Use your reference tables to help you out. All right, so now that you've had a chance to probably go through those questions and give them a shot, I'm going to share with you the answer key on the next page. If you want to, take a screenshot or pause the video, take your time, whatever works best for you. Check your answers. Ignore the gaff. You know how it is when I've got two markers in my hand and I forget I'm writing with both hands, and then I don't put one down. Typical me. All right, so let's head back. All right, so in terms of the life cycle of a star, after it's created and becomes a main sequence star, it goes throughout its life burning, not really burning, but fusing hydrogen and helium. Eventually it gets to a point where it's exhausted its hydrogen source. It goes to helium. It might start to bloat and get bigger like a big red star, kind of like indigestion. All right, and then eventually over time, depending on how big that star is originally, you end up with either cataclysm or just simply a sad candle waning away. So let's look at the two different pathways. And this is going to be a lot nicer on your screen if you're using the color version that's inside of the shared folder. But let's start with the nebula, all right? We've got that nebula and the gas that's collapsing due to gravity, building up all that pressure and temperature inside, and then you get that boom, it turns into a main sequence star. From that main sequence star, you can either start to die as a red giant or a red supergiant. So our star, the sun, is traveling down through this pathway here. However, you may have read in the news or have heard in the news or watched in the news or somewhere in the news, you've heard about Betelgeuse. Betelgeuse is a giant, supergiant red star, almost the size of our solar system. And people were trying to figure out, is this thing about to explode because it was doing this dimming process? And there were some questions about it. As of right now, it doesn't look like it's about to explode, but estimates think maybe in the next 100,000 years, we're going to get a massive explosion, and you might actually have something you can see in terms of light during the day with our sun in the sky, and then maybe something at night that is as bright as the moon. So some very interesting, maybe future whatever, you know what I mean? Like, all right, future explosions. All right, so here we go. The red giant turns into just a planetary nebula. So eventually this thing just runs out of fuel and just goes, and it just kind of wisps away. And what's left over in the center of that red giant is a little white dwarf. Okay? It's probably like a tenth of the size of our star right now. And like a candle, when you blow it out, you have that little ember on the wick that's burning a little kind of like glowing, giving off light, and eventually it starts to wane and get dimmer, dimmer, dimmer. Then it's gone, and it's just a little piece of charcoal that used to be the string. That's what happens to our star, the sun. It ends up turning into a black dwarf, just a lump of carbon, like a lump of charcoal, just floating through space. Yeah, I know, not the most interesting. However, let's go to a new one. A little bit about what I was talking about with Betelgeuse. It will explode. And as we see it, it's most likely to make a neutron star, which means literally explosion, shove neutrons together. Things that have no charge, like magnets. Magnets have a plus and a minus, they have poles. And those pluses and minuses, they stick together. Now, neutrons, when you get to chemistry, don't have a charge. But yet, there is so much force from this explosion, it causes the neutrons to stay together. So you end up with a neutron star. Typically, a neutron star has a diameter of like Manhattan. They're really small. Like a teaspoon of this stuff is going to weigh like 272,000 Empire State Buildings. Teaspoon. Nuts. Black holes. That's what everybody wants to know more about. If you want to know a lot more, take astronomy. Maybe I'll try to put a video below if you're interested in black holes, and you can watch that. But black holes, we're talking about in a massive explosion, saying all that energy and mass down in this tiny little pinpoint. And it's so small that not even light can escape, because it's bending the curvature of space-time, so that stuff just travels right in and doesn't get around it. Absolutely crazy. All right, so we've had some practice here. We talked about the life of the stars. We practiced a little bit of luminosity versus temperature. So let's go ahead and start working on guided question number 1 and 2. Pause the video, use the access point if you need it, and your notes. Just in case you want to watch. All right, so base your answer to this question on the table below and your infinite knowledge of Earth science. The table shows the velocities in kilometers per second for several galaxies, represented by letter A, B, C, D, and E, that are moving away from Earth. Okay, so the away from Earth. Okay. The vast majority of stars and galaxies in the universe are moving away from our solar system. Scientific evidence indicates that the farther away a galaxy is, the faster it's moving. All right, so we might need this background information, we might not. Let's look at the data. Velocity of galaxies moving away from Earth. Galaxy A, B, C, D, E. Velocity away. All right, a star in one of these galaxies has a surface temperature of 8,000 Kelvin and a luminosity of 10. Identify the stage and color of this star. When they say stage, they mean main sequence, white dwarf, giant, supergiant. So stage of life for that star. And each of those different portions of the diagram are stages of life. So normally it stays on the main sequence and then it bloats up the giant or bloats up the supergiant, and then either they explode and send way back down here where there's very little light, or you might be a giant where you start to fizzle out down here. All right, so we were talking about 8,000 Kelvin. Thank goodness they gave us a number that is actually right on the scale. So here we've got 8, I'm going to use a different color as I should, 8,000. Okay, almost nailed it at the top. So 8,000 Kelvin, it's white. And did they give us a luminosity? I think they did. I think they said 10. All right, so luminosity of 10 is here. So let's see where they meet. So it is a main sequence star and white in color. So let's make sure we get that down. So main sequence and white color. That is the star they were talking about for these galaxies. All right, let's go to the next question. Number 2. Número dos. Love it. Woo, this is a big one. Woo. All right, so let's start with that. All right, so base your answer to the question on the graph below and your infinite knowledge of Earth science. The graph shows the changes in a single star's luminosity and relative temperature from its formation. Point 1. So a single star, one star, luminosity and temperature from its formation, beginning of its life. Point 1. So here's point 1. To its late stage, point 4, relative to the sun. So here's 1, 2, 3, 4 positions relative to our sun. So it's not our sun we're talking about. Similar chart and graph, everything we have from our reference tables. Oh, I'm doing it again. Let's move up to here. Which table correctly classifies this star at points 3 and 4? So we have to figure out what it's called at point 3 and 4. So we got to look and see what type of stars are here on our reference tables, what type of stars are here on our reference tables. So we go back. That's where 3 was. Here's where 4 is. And that was the sun here as a reference point. So that we realize that 3 is in this area away from the sun. And 4 is this direction away from the sun in the diagram. So we come back to here. Let's figure out what works best. So 3 being giant, 4 being white dwarf. And we got that one right there. Choice 1. All right, so that brings us again to another end of another episode, another lesson of Earth science based on the life of stars and the characteristics of stars. Try to finish up these independent practice questions with your access points. Again, if you have questions or you have concerns, you can hit me up on the comments below on the video. I'll try to respond to those. I'll hit you up on WebEx. I'll hit you up on Google Classroom. I'll hit you up everywhere.